go ahead and capture. All right, so I will get those graded as soon as possible. It's probably going to take a few days because normally weekends I can spend grading, but during the week I'm teaching all day, so it may be a few days before these get graded. But I will get them graded as soon as possible, and I will post feedback in Canvas. If you lost any points, telling you where point deductions were. I still have office hours this week as usual. I'll be moving my office hours probably starting next week, but this week they're the same as usual. So if you need to talk about homeworks or labs or concerns on the midterm, catch me during office hours, and we can go over stuff. All right, so any questions on the homework? I'm hoping to go over Lab 5 today, but I also want to go over a few things from the homework related to modulo counters. But any other questions on the homework? And let me start up my Zoom on my other system here, in case people have private questions.
I have a question about the state diagrams and how to incorporate whether it's a Mealy or machine.
Okay.
How that changes the state diagram.
Yeah. So the main difference is the following. When you have a state machine, sometimes your output is just a function of your state, and other times your output is a function of the state and one or more inputs. Okay, if your outputs only depend, all of your outputs only depend on the state, that's called a Moore machine. If your output also depends not just on the state but the inputs, that's a Mealy. Okay, for a Moore machine, since the output only depends on the state, we can draw our state pictures like this. Right? We can draw a circle, we can list the name of the state, the values of the flip-flops, and then right underneath that we can list the outputs. And that's unambiguous, because if you know what the state is, you should know what the outputs are. But for a Mealy machine, you need to know not just the state, but also what the inputs are. So on the transition arrows that list the inputs, we also list the output next to that. So a Moore machine, our arrows would just be labeled with the inputs showing what state we're going to. On a Mealy machine, the arrows are labeled with the input and also what the output value is. So this is saying if you're in this state and this is your input, that's your output value. And whether it's Mealy or Moore really just depends on what you find when you analyze the circuit. When you look at your Z equation, if it depends just on the states of the flip-flops, then it's going to be a Moore machine. And in practice, some outputs might be Mealy outputs and some might be Moore, but first order, right, if any outputs depend on the inputs, call it a Mealy machine and use this to show your state transitions and your outputs.
So either way you show the outputs, it just depends where you put the outputs.
Exactly, yeah. And you could always show it like this, right? But it's simpler if the input doesn't affect the output, just list the input right there in that bubble.
Oh, okay. All right. Thank you.
All right, cool. All right, so these questions take a long time, right, on the midterm, and there's this extra wrinkle of having to do the upload part, which was what the practice was there for partially. Is it okay that you refocus the monitor? Like that. And let me actually double check and see if my resolution, yeah, my resolution's good. Okay, cool. Alright, so yeah, if you ran out of time, hopefully you got uploaded what you already had. If for some reason you ran out of time and you did not get your stuff uploaded, email it to me right now, okay? Go back and watch the video later. Hop onto you know, your machine and just email me what you have, and I need to get it like right away, because if I get it in 2 hours, I don't know if you spent 2 hours trying to upload it or 2 hours also doing work. So seriously, if you did not get your stuff uploaded during the exam, take your files, email them to me right this second, so that I have them as soon as possible. Alright, so 2.5 hours, yeah, that's a long time for an exam. How would you determine the timing diagram for 1U? Alright, let's take a look at the homework set. So I'm not going to give you a procedure for this, because what I want you to do here is explore this circuit. Okay, so suppose an initial value for S and an initial value for R. Figure out what the value for Y is, and sketch those. You know, sketch what S is, what R is, and what Y is. And if it's changing, you know, show me that Y is changing, and then change S to a different value and see how Y responds. And then change R to a different value, and then maybe change S and R back, and try to capture different combinations of S and R, but also different orders of sequences, because these are sequential circuits. It's not just enough to say if S is 0 and R is 0, Y is this. It might depend on what happened previously. So try to see what the different behaviors of this circuit are, and then come up with a set of values in sequence for S and R that illustrate the different things this circuit can do. In other words, if S and R are both 0, maybe Y is sometimes 0 and sometimes 1. So come up with an interesting timing diagram that covers as many different possibilities as you can think of, in as many orders as you need to sort of show the whole behavior of the circuit. And it's really an analysis question, right? It's asking you to study this circuit and try to figure out what it does, and then make a timing diagram to illustrate that. And the timing diagram is just, you know, this graph where time runs horizontally, and you just show the values of S and R, high or low, and the value of Y that corresponds to it. All right, other questions? All right, so let me talk about one of the other problems in here. So I posted a video last week about timing of state machines. That's what question 3 is about. It's basically, you know, this period before the clock tick, that's the setup time. The period after is the hold time. Okay, and if you read question 3S, this is a timing diagram that shows you these periods during which the input needs to be stable. So 3U, you're doing the same thing, but for a particular input sequence, 1, 0, 1, 1, 0. So you're drawing a timing diagram that shows the values of this EI input that respect these setup and hold times. Question 4 is one of these think about questions. If you have a D flip-flop and you want a T flip-flop, how can you make that happen? Right? So if you have a positive edge triggered D flip-flop and you want a negative edged, just invert the clock. But if you have a positive edge D flip-flop and you want a positive edge toggle flip-flop, how do you do that? And it's going to involve, you know, some combination of using the output and the T input to drive the D input. So experiment with that one, see what you come up with. And then question 5 is again looking at setup and hold times and basically completing a timing diagram. So show what Q does in response to these clock changes in the S and the R. And then 6 is this is a more scripted version of question 1, where you're just given a circuit and you're asked to construct the timing diagram. So maybe do question 5 first, right, where you're given specific values for the inputs in the clock and construct the Q, and then from that maybe go back and try to do question 1. Alright, 6 we talked about a bit in class last time, and it's an analysis question. Same with 7. Question 8 talks about modulo counters, so let me do some detail on that. So what is a counter? A counter is a sequential circuit that outputs a particular pattern of ones and zeros, typically a pattern that counts in binary. Okay, so a typical 3-bit counter might, for example, produce the following outputs. Where this is, say, Q2, Q1, and Q0. And each time the clock ticks, the outputs will change to what we would see as the next binary value, 0, 1, 2, 3, 4, 5, 6, 7, and then rolling back over to 0. Okay, so this would go by a number of names. This would be a 3-bit counter. Sometimes it would be called an up counter because it's counting up, and you could count down as well. It can also be called a modulo 8 counter. So if you think back to CSE 121, if you've done it, or maybe other classes, this idea of modulo is basically saying mod 8 says let's only consider values from 0 to 7. Okay, so a mod 8 counter goes from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. And then it goes back to 0. A modulo 9 counter would only go from 0 to 8, and then after it counted to 8, it would go back to 0. That would have to be a 4-bit counter. A modulo 3 counter would count something like this, 0, 0, 0, 1, 1, 0, and then it would go back to 0, 0, 0, 1, 1, 0, and so on. So that's a modulo 3 counter. And the other way to think of it is there are 3 distinct outputs that you get in this counting sequence. So for the solved question, it asks what is the mod of this counter, and you do an analysis and you find that it counts from 3 to 4 to 5 to 6 to 7, and then to 8, and then back to 3. So this solved problem has outputs 3, 4, 5, 6, 7, 8. 6 different outputs. That makes it a mod 6 counter. Okay, it can be used to count from 3 to 8. And then it asks, could you make a mod 9 counter out of this? And if you analyze this circuit by grounding out A and B, this will actually count 3, 4, 5, 6, it'll count 0, 1, 2, 3, 4, 5, 6, 7, 8, and then back to 0. So that becomes a mod 9 counter, 9 different values. So let's look at this binary up counter and see what it's doing. It's got a clock coming in, okay, and the clock causes it to move from one value to the next. And a straight 4-bit binary up counter just counts in binary, right? So it tells us QA is the least significant bit, QD is the most significant. So it's going to count in the following sequence. Right, that's what a 4-bit up counter will do. So it will count a total of 16 values in binary from 0 up through 15. right? And we were told QA was the least significant bit, QD was the most. And then once it gets to its largest value, which is all ones, it rolls back over to all zeros, and it continues counting from there. So that's what this block by itself does. Okay, and it clocks when the clock input ticks from 0 to 1. Okay, this particular up counter has an extra pair of inputs. It has an input labeled CLR, clear, and it says clear will set all outputs to 0. Clear bar will set all outputs to 0. So if you were to put a 0 into this line, all of these outputs go to 0. It's a reset option. Okay, well this input is tied to 5 volts, so clear is never set to 0, so that has no effect. The load line, on the other hand, when load is asserted when it's equal to 1, it takes these 4 inputs and loads those into Q, A, B, C, and D. So that's a preset option. And anytime the load line goes high, these 4 input values will get loaded into the internal count. So for example, maybe I'm counting 0, 0, 0, 0, 0, 0, 0, 1, and maybe my inputs A, B, C, D are set to 1, 0, 1, 1. If I assert the load line, the next count that I'm going to get is 1, 0, 1, 1. Okay, in other words, the values of A, B, C, D will become the value of the counter. So it's a preload option. Okay, so this is an up counter. Counts in binary. It has 4 bits. Every time the clock ticks from low to high, it counts to the next value. But if the load line is high, the next count will not be the next sequential count. It will be whatever the value of A, B, C, and D are. And if the clear line is pulled low, the next tick will set everything to 0. Okay, the last thing is you're told that these inputs are synchronous, which means they don't do anything until the clock ticks. So I can set the load line high, I can set the clear line low, which should definitely change my outputs, but nothing will actually happen until the clock tick. And if when the clock ticks, this is not asserted and that's not asserted, then they have no effect. Okay, that's what synchronous means. If you have asynchronous inputs, then for example, the moment you assert the clear line, immediately the outputs go low, even if you haven't ticked the clock. Okay, so asynchronous inputs happen immediately without regard for the clock. Synchronous ones only take effect when the clock ticks. So use those ideas to analyze this circuit, convince yourself this is what it does, and that if you made this change, then it would count from 0 to 8. And then with that in mind, look at this circuit. Okay, it's still an up counter, it's still got 4 outputs, it's got the synchronous clear bar and load, but this time the input is set to something different. Okay, the A, B, C, D lines are set differently, and the Q, D output still goes to the load line. So analyze that and see what it does. And then 9 is a timing question that's talked about in the video, and then 10 and 11 are state machine analysis questions. So that should be enough to make a good stab at all of the homework questions that were assigned. So any other questions on homework? All right, so I've adjusted due dates for the next homework. So homework 5, isn't this week 5? Yeah, I think this is week 5. Why? The week numbers have nothing to do with the lab or homework numbers in general. If they do, it's coincidence. But let me show you what I've done. So homework 5 is going to be due a week from tomorrow. Okay, homework 4 is due tomorrow. Homework 5, which is chapter 5, will be due in a week. And we may get started on that today, but possibly not. But definitely we'll have Thursday to spend talking about state machine synthesis, which is what this homework is about. And then we can talk final details on that next Tuesday, and then it's due the day after. So we'll have at least 2 full class periods to talk about the material for homework 5. And then lab 5 I've pushed back to the 25th, which is on a Monday. Okay, so I want to start talking about lab 5 right now. I want you to be able to ask more questions about it Thursday, and then have the weekend to work on it. All right, lab 6 will not be due on the 29th. I'll move these dates around as we go forward, and homework 6 will not be due the 29th, so I've taken that off for now, but I'll put it back depending on where we get to in the next week. So we'll still have more homework coming, but the dates will get moved back. Let me see. Oh, we got a good number of people here still. Good. All right. So let's talk about the lab. So lab 5 is dealing with sequential circuits with clocks. And a few experiments in here to get our feet wet. So first experiment is dealing with a totally different kind of chip. Okay, this is a chip called a 555. We touched on this briefly a few classes ago. 555 is what we call an analog chip. It's not digital per se. It gets hooked up with resistors and capacitors, and it does all these crazy things. But the way we're going to use a 555 is in what's called an astable operation. This is a state where it will switch back and forth between 2 states. And in these 2 states, it will output either 5 volts or 0 volts. So we're going to use this to generate a pulse of 1s and 0s. And we'll use this, a fair amount in this class. We'll use it in lab 6. You'll use this to drive your final traffic light design with the yellow lights. And you'll also use this in Engineering 270. At least we used to. I don't know what we're going to do for labs for summer online. But you'll encounter this chip a lot, okay? So really simple chip, 8 pins. We don't even use all 8 of them, okay? So pin 1 is connected to ground, and pin 8 is connected to VCC, 5 volts. And you don't see that usually you don't always see that in these wiring diagrams, okay? This one you do. So you want to wire up your chip like this. And be really mindful when you wire this up, because there's a lot of wires here. Okay, pin 1 goes to ground. Pin 2 goes through a capacitor to ground. Pin 3 is your output. Pin 4 goes to VCC. Pin 5 doesn't get used. Pin 6 gets connected to pin 2. Pin 7 goes through a resistor to pin 2 and another resistor to VCC. Pin 8 goes to the VCC and also through a resistor to pin 3. Okay, that's easy to say. It's harder to wire up. But basically wire this up. This little 0.01 microfarad capacitor we're not too worried about. So how do capacitors work? Capacitors, maybe we touch on them in 120, maybe not. It depends who's teaching and how much time there is. But a capacitor, really interesting device. So the symbol for it is this, and the way a capacitor is set up physically looks like this. It's typically 2 plates of metal with a wire coming off each one and no connection between the 2 plates. There's a gap here. It could be air, it could be a little piece of mica, it could be cardboard, it could be some goopy chemical, but there's something that's preventing a physical connection from this side to that side. So if you put 5 volts on this side and connect that side to ground, what happens? Nothing, right? Current cannot flow from here to here because there's no connection. The metal doesn't touch. But it turns out if you put in a voltage that changes over time, you actually get a current flow. And that's kind of freaky. So that's one thing that these things do. They allow current to flow depending on how fast the input is changing. Now, if the input doesn't change, no current flows. If the input changes quickly, a lot of current flows. The other thing that these do is they store charge. So you can put a time varying voltage into here, right? And it will build up a charge inside this space between the two plates. If you get a big capacitor and you charge it up and you touch it, you get shocked. Okay, this is why things like TV sets and stuff say, no user serviceable parts inside, extreme danger, do not take apart, right? Because if you have like an old TV set and you unplug it and you put it out on the curb, and 3 days later someone comes along and takes the back off and starts looking around inside, they can get a really nasty shock. Because these things store up charge. And there's some really big capacitors in things like TVs. Yeah, that is how old TVs, that was their thing. Okay, you can also use these, like if you have a car with a really good car stereo in it, with really good bass system, you may notice every time that your bass thumps, your headlights dim, right? Because your battery and your generator can only put out so much current, and to move the cones of the woofer far enough to push out the air that you need for that good satisfying bass tone takes a lot of current, and it can pull enough current that the battery can't supply it, and the headlights visibly dim. So it's a feature or a bug depending on if you like your headlights strobing to your music. So what you can do is you can buy these big capacitors that you basically put in line with your electrical system, and in between those bass beats these things build up charge. And then when the woofers want a lot of current to move, the extra charge comes from these capacitors. So if you look on Amazon for like capacitor bass car, you'll see these things for sale. Okay, and that's what this capacitor right here is doing. This is right here to basically deal with fluctuations in the power supply. Because look, it's connected between ground and 5 volts. Well, we don't normally connect things between ground and 5 volts because that seems like a short. But there's no connection between here and here because there's this air gap inside the capacitor. But if the voltage supply starts to fluctuate, if it starts to drop a little bit, this thing will actually supply extra current, bring the voltage back up to 5 volts. Now this is not critical in this circuit, but in 270, again, maybe not on the simulation, but in 270 when you're doing things like driving motors, these become really, really important. Because in a theoretical sense, this is always 5 volts. In an actual laboratory, this will bounce all over the place. It'll go down to 4.5 volts, maybe 4.2 volts, maybe up to 5.5 volts, right? And that can really confuse circuitry, especially if this is a microprocessor. This capacitor here is being just used to store charge to control the timing of this device. And if you're in the electrical engineering sequence and you take 204, 252, 253, you'll learn all about these things and how to analyze them. But basically you can use these things to build a circuit where your voltage does something like this. It drops off slowly, or maybe it rises slowly. So that you might close a switch and instead of the output immediately going to 5 volts, it slowly rises over, say, half a second. And it's that ability to slowly change voltage as an exponential function that lets this and the circuitry in here oscillate. Okay. So could a capacitor be used to prevent damage to components inside by storing the excess charge when connected to ground? Yep, exactly. That's one of the key uses for capacitors, is to absorb excess voltage. If you look on, like an old motherboard from a desktop computer, you'll see it covered with all these tiny little, usually they're light brown colored rectangles or squares. Those are all tiny little capacitors. And you put them everywhere. Just about every place that you have an input or output, you'll see a capacitor, and it's there to manage the realities of physical circuits. the excess voltage or the low voltage. Alright, so that's a lot of theory and background, none of which you technically need to make this circuit work, okay? All you have to do is faithfully wire this circuit like this with the following values. Your capacitor is 1 microfarad, your two resistors are 1 mega ohm each. And if you wire your circuit like this, the output will change according to this formula. The output will go high for about 0.7 times RA plus RB times C, and it'll go low for 0.7 times RB times C seconds. Now these are 1 mega ohm each, and this is a microfarad. So this is 2 million times 1 millionth. This is about 2. So wired as it is with these values, output 3 will be high for about 1.4 seconds and low for about 0.7. So you'll see it oscillate, and it'll be on for about twice as long as it is off, and it'll take about 2 seconds to cycle through. And if you actually got a 555 and wired this up and put an LED on here, it would blink on and off very slowly every 2 seconds. It would go on and then off. Alright, so build this circuit in Tinkercad, look at it, maybe use the oscilloscope, right, and sketch what the waveform looks like, okay, and then explain why or why not that was what you were expecting it to look like, okay. So that's an introduction to the 555. The second experiment, we actually use this to drive a counter. So we're going to use a 74HC93. Let's take a look at that. Let's take a look at that. So 74HC93, that's a 4-bit binary counter. And the data sheet lists a pair of chips. This is the 7490, this is the 7493, so we want this one on the right. Okay. So using this, the clock generator from the previous experiment, and the 7-segment display, implement an up counter. So the counter should count from 0 to 9 and then back to 0. Alright, and definitely consider using the 4511 to convert the binary data to the 7-segment display. Alright, here's my daily spam call. Alright, so how are we going to do this? Let's look at this chip. So this chip has a pair of inputs, has a few pins with no connections. It has outputs QA, QD, QB, QC. Ground on pin 10, power on pin 5. That's different. Okay. And then these two inputs, RO1 and RO2. Okay, go to the truth table or the function table. And make sure you're looking at the 93. Okay, so there's the 93, here's the 93. Okay, so the 93 has a reset option. If RO1 and RO2 are both high, the output is all low. That's the reset state. We're not interested in resetting this thing. Okay, so if we make any of these inputs low, then the system will count. So best advice, just take both of those inputs, tie them to ground. RO1 and RO2, just connect them both to ground. And now your 7493 is going to count. And here's the counting sequence. Okay, so every time the clock ticks, it'll go from, all zeros to 1 to 2 to 3, all the way up to 15, and then back to 0. So put these two inputs low, connect power and ground, right? These are your 4 outputs: least significant bit, next, next, most. And the last thing we have to look at is input A, input B. And this is endlessly confusing. So here's a 7493. Input A is the input to one JK flip-flop, right? Which will basically count. Okay, most important thing to know about this lab. If you do this, life will be great. If you don't, you're going to be trying to figure out what's going wrong. When you take your 7493, connect QA to input B. Make a wire between pin 12 and pin 1, and then use this as your clock input. Okay, tell your friends if you like them, and they'll thank you. So 74 LS93. I'm writing this down and then I'll switch to this view. QA pin 12 should go to input B, which is pin 1, and your clock should go to input A, which is pin 14. Okay, wire it up like that. Feed your clock to pin 14 and connect pin 12 to pin 1. And then your output is going to be it's going to be QA is the least significant bit, QB, QC, QD. QA is pin 12, and then 9, and then 8, and then 11. So this is the least significant bit, this is the most significant bit. Alright, and these are the outputs that you're going to send to your decoder and then to your 7-segment display. Alright, so this is the critical piece that's not spelled out in the lab, but it's spelled out in the data sheet if you know that it's there. And this makes it a true 4-bit binary counter, because normally this is a 3-bit counter and a 1-bit counter. Right? So this thing up here is just a 1-bit counter. Input A drives QA, it toggles between 1 and 0. And this is a 3-bit counter, and they have nothing to do with each other. The way you connect them to make a 4-bit counter is feed QA to input B. Okay, and then put your clock in there. So we're most of the way there. Okay, that will let you wire this counter up. The clock comes from pin 3 on your 555, right? Build your 555, put an LED on here, make sure it's blinking. And now if you connect that to pin 14, right, you'll be driving this 4-bit counter using your 555. And after 16 seconds, roughly, right, this will have counted through all 16 values. Okay, here's the last trick. You want the counter to count from 0 to 9 and then back to 0. By default, this is going to count from 0 to 15 and then back to 0. So think about the homework question related to counters. And think about this and ask yourself, how can we make this count from 0 to 9, and then instead of going on to 10, go back to 0? And the answer will have to do with these reset inputs. Okay? So if these are tied to ground, you have a 4-bit counter goes from 0 through 15. But if you hook that up to your display, you know it'll just show you on that 7-segment display 0, 1, 2, 3, 7, 8, 9. And then it'll go blank for the next 6 counts, 10 through 15, and then it'll go back to 0. So after you get to 9, you would like the next clock tick to go back to 0. Well, you can use these reset inputs to do that. So do something so that when it's at a 9, the reset line turns high, and then it will go ahead and it will reset it on the next clock tick and go back to 0. So it's implementing what you were doing in those clock questions for the homework, those counter questions for the homework. All right, so that's the lab, 2 experiments, right? First one is just building the circuit, looking at what it does, looking at the waveform it generates, drawing it, right? And then explaining any differences between what you observed and what you expected. And then the second one is connecting that counter, that timer to a counter, connecting a counter to a decoder, decoder to a 7-segment display, and making it count in sequence. Okay, and for this you need to have a system diagram, right, with inputs and outputs, detailed schematics, so show me where you're making your connections to, what pin numbers, and so on. and make a timing diagram. Okay, so timing diagram that shows the what's coming out of pin 3, what's going into input A, and what these outputs are doing. Okay, so combinational circuits, traffic light controller, we draw truth tables to explain what the behavior is. For these time varying circuits, these sequential circuits, we draw timing diagrams. Okay. And test plan, basically just show me some screenshots of your circuit counting. Okay. So I definitely want to see the detailed schematic with wiring information, so pin numbers, part numbers, timing diagram of what the output should be, and then show me a few pictures of your circuit working. Okay, so implement and test on Tinkercad. And then the usual stuff, cover sheet, lessons learned, new experiment. You're good to go. Lab 4 looked really good, by the way, okay? Really big improvement from everybody on presentation and what was included in the lab and so on. I was so happy grading those. Just looked really solid. So I think people are moving in a really good direction with lab reports, and that's awesome, because that's going to help you a lot down the road. All right, so questions on lab 5. All right. So let me tell you where we're going. So we've been analyzing state machines, right? We've been given something like this. Something like this, and asked to figure out what this machine does. So we write equations for flip-flop inputs and for the output. We make that big, long present state, next state table. We turn that into a diagram, and we end up with something like this, right? Or something like this. Okay, that's the analysis part. Where we're going next, and we'll dig into this full force on Thursday, is synthesis. It's the exact same thing, but in the reverse direction. So we're going to begin with a diagram like this and try to develop a circuit like that. And so how do we do that? Well, we take the state transition diagram. From that, we build a table which says, if we're in this state and our input is a 0, then our output should be a 1, and we should go to that state. And we fill in this table from the diagram. And then, using what we've known from the beginning of this course, we write equations for these inputs based on what we want the flip-flops to do. So if we're told that we're using JK flip-flops, and we know that the current value is a 0, and we want the value to be a 1 after a tick, what should we set J and K to? So we fill in this truth table, and then we write equations for these. And once you have equations, you can sketch a circuit diagram. All right, so that's the other direction. And it's generally more complex doing synthesis because you're starting with really nothing. You're trying to come up with something. But the steps are going to be the same. They're just going to go in the reverse order. So everything you've done in working on analysis will help you in doing synthesis. Okay, but the synthesis questions generally take more time. They take bigger sheets of paper, finer points on your pencils. But it's nothing that we can't do. All right, once we've done state machine synthesis, which will take us about a week, then we're going to completely switch gears and we're going to wrap up the course talking about something called Verilog. Verilog is a hardware definition language. Okay, it's a way that we can do all the stuff we've been doing by writing stuff that looks like programs. Okay, now it's not programming, it's not writing C programs, but what we do is going to look like we're writing C programs. We're really going to be writing code that describes circuitry, like this. And we're not going to describe the circuitry by saying, you know, take an inverter and an AND gate and send the output to an OR gate and send that to a flip-flop, right? We can do that in Verilog, but we can also do things like, I want a circuit that, you know, when I'm in state 0 and the input is 0, moves to state 1. And we can code that up with like a case statement or a bunch of if statements. And Verilog is a really fun way to design and implement digital logic, and it's very different from what we've been doing, but you have to understand what we've been doing to be able to write Verilog, okay? So it's like the difference between doing derivatives with, you know, f of x plus delta x minus f of x over delta x, right? Versus, you know, derivative of x squared is just 2x to the first, okay? It really kind of like gives us a much more powerful way to design these circuits using what we already know, but in a much more fluent form. And most of the design work that's done out there is done in Verilog or some other hardware definition language. And if you want, you know, to come out of school and get like 6 figures right away down in the valley, get really good at Verilog, right? Go ahead and look at jobs for Verilog designers, and you see some really good salaries. And it's a lot of fun. So we'll do next week, or for the next week, starting on Thursday, we'll do state machine synthesis, and then we'll segue over to discussing hardware definition languages, Verilog in particular. All right, I'll get exams graded as soon as I can. I'll get comments posted. Catch me in office hours if you need. Otherwise, I will see you on Thursday.